Hi all, this is Rohit and I was doing a master's in computer engineering and today I'm going to present a topic on types of semiconductors. In this presentation we are going to learn about definition of semiconductors and types of semiconductors. And in the types of semiconductors there are two types of semiconductors. One is intrinsic semiconductor and extrinsic semiconductor, and even applications of semiconductors and advantages, disadvantages, and at the end conclusion. So now definition of semiconductors. In semiconductors, the word conduction is known as rate of flow of electrons. And based on these conduction properties, they divide it into three different parts. The first one is metals. In this, flow of electrons will be high, so the conduction will also be high. For example, from the current source, if we connect a wire to any other devices, we use a copper wire, and the copper wire is a metal. So the flow of electrons will be high in metal. And the second one is insulators. In this, the flow of electrons will be low, so the conduction will also be low. For example, like rubber or any wood. So the conduction properties between metals and insulators is known as semiconductors, and they have conductivities in a range of 10 to the power of minus 4 to 10 to the power of 4 Siemens per meter. Types of semiconductors. There are two types of semiconductors. One is intrinsic semiconductors and the extrinsic semiconductors. And intrinsic semiconductors is known as pure semiconductors, and extrinsic semiconductors is known as impure semiconductors. Intrinsic semiconductors. Intrinsic semiconductors are pure materials, typically silicon or germanium, and with no intentional impurities added. And the conductivity of intrinsic semiconductors is sensitive to temperature changes and increasing as more electrons gain the energy to move from valence band to the conductive band across the band gap, which is about 1.1 electron valence band for silicon. From the first picture, each silicon atom is shown with its valence shell and the sharing of electrons with neighboring silicon atoms to form covalent bonds. And this sharing of electrons is crucial for stability and structure of a crystal lattice in silicon and for the common semiconductor of materials. And the dotted lines indicate the outermost shell of the electrons that participate in the bonding. And for the second picture, the energy bands in the semiconductor representing the conduction band, valence band, and the energy gap between them. And the Fermi level is marking the chemical potential for electrons. The valence band is the lower energy band where electrons are present at zero temperature, and the conduction band is the higher energy band that electrons can move to gain sufficient energy. Extrinsic semiconductors. Extrinsic semiconductors are created by doping pure semiconductor materials such as silicon or germanium with specific impurities to enhance their electrical properties. And this process involves adding either pentavalent impurities like phosphorus or arsenic to produce n-type semiconductors, which access electrons as majority charge carriers, and to create p-type semiconductors where holes are predominant. And based on these impurities present in the extrinsic semiconductors, they are classified into two categories. First one is n-type semiconductors and the second one is p-type semiconductors. N-type semiconductors. An N-type semiconductor is made by doping an intrinsic semiconductor such as silicon with the pentavalent impurities like phosphorus, arsenic or antimony. This doping process introduces entire electrons like negative charge carriers into a semiconductor, enhancing into electrical conductivity. The major charge carriers in n-type semiconductors are these free electrons, as opposed to the holes in p-type semiconductors. N-type materials are crystal in forming of p-n junction diodes, a kind of diodes, when combined with p-type materials, leading to creation of essential electrons components such as diodes or transistors, which are integral to wide array of modern electronic devices. N-type semiconductors. And in the first picture, it is representing the process of doping in a semiconductor, specifically using an impurity atom in a silicon crystal lattice. The impurity is shown in antimony, which replaces a silicon atom in lattice. And when coming to the second picture, it represents the energy level in a doping semiconductor, and it includes the valence band, conduction band, and the donor level, which lies just below the conduction band. P-type semiconductors. A P-type semiconductor is created by doping an intrinsic semiconductors, typically silicon or germanium, with a trivalent impurity such as boron, aluminium, or gallium. The process introduces holes or place where the electron is absent and which act as a positive charge carriers. In p-type material, these holes are majority carriers and they move through the lattice of a semiconductor by hopping from one electron to the site of another electron. This movement of holes facilitates the flow of current of the opposite direction to the most of the electrons in the n-type semiconductors. The p-type semiconductors are used extensively in electronic devices, forming p-n junction with n-type semiconductors to create diodes or any transistors and other crucial components. The combination of p-type and n-type semiconductors is fundamental in controlling electrical properties and behaves in various electronic applications. P-type semiconductors. In this, the first picture, it represents the P-type is doping in the semiconductor using boron as an impurity atom, and it is also known as an acceptor. And the boron, which has three valence electrons, that replaces a silicon atom in the silicon crystal lattice. The boron atom bonds with surrounded silicon atoms but lacks one electron to complete the bonding network, and it resulting the hole. And from the second picture, it represents the valence band and the conduction band are shown along the acceptor level, which is located just above the valence band. Now coming to the applications of semiconductors. Semiconductors are the building blocks for microprocessor chips and transistors used in computers, laptops, or any other computing devices. And these components are essential for processing and storing the data in a digital information. And it is used to manufacture photovoltaic cells in solar panels. And these cells convert solar light into electricity by exploiting the semiconductor's ability to absorb light and convert into the electrical energy. And the next application is LED and organic LED use semiconductor materials to create more energy efficiency in lighting. And coming to the last application, and it is widely used in medical devices, which includes diagnostic equipment like MRI machines and devices like pacemakers. And pacemakers, it is used to monitor the heartbeat of a humans or any other living beings. Advantages of semiconductors. Semiconductor devices are significantly more compact and less weight compared to the vacuum tubes. And these devices typically have much longer lifespan than vacuum tubes. And these devices are generally less expensive and consume less power than vacuum tubes. And the semiconductor devices can function both conductor and insulator depending upon the temperature changes. And when coming to the lifespan, it has a very longer lifespan with fewer failure rates due to solid state construction. And now coming to the disadvantages of semiconductors. Semiconductor devices are very sensitive. to change for temperature, whereas vacuum tubes has less sensitive. And the semiconductor devices are not able to handle as much as power as vacuum tubes. And the noise level is too much higher in semiconductor devices as compared to the vacuum tubes. And it has a high frequency range and they have poor performance. Conclusion. Semiconductors are integral to modern electronics due to their ability to enable the development of smaller, faster, and more efficient devices. Their low power consumption and high reliability make them ideal to a wide range of applications from everyday gadgets to complex computing systems. Thank you.